Hello everyone, welcome to my YouTube channel. And as in the previous video you saw, we were working on increasing our coding and simulation skills, specifically in vapor compression cycle, which is used in HVAC, refrigeration, different heat pumps. And we have studied single looping and we have studied multiple looping, and now we will move forward and we will try to go more deeper into thermodynamics of this vapor compression cycle. And in this video we will try to study the second law of thermodynamics. That is, we will try to check that can Grok calculate the exergy efficiency of the system, and can it calculate the exergy destruction of the cycle. So let's see, and we will ask Grok, please modify the code so that we can get plots of evaporation temperature versus COP, Exergy efficiency, and total Exergy destruction. Also provide these results in an Excel file. So let's see that can Grok calculate this exergy efficiency, exergy destruction, which comes under the second law of thermodynamics. So what it says, it will modify it, coefficient of performance, exergy efficiency, total exergy destruction against the evaporator temperature with the 5 degree C step with all these refrigerants, and the other parameters it will keep constant as baseline, that is condenser temperature 40, superheating and subcooling 5 degrees Celsius, and isentropic efficiency 0.8. So it seems quite well. So it will provide its subplots in three plots, which is COP, exergy efficiency, and exergy destruction. But we want to see, like, can it calculate these things correctly. So here we can see it has also provided us the formulas for exergy efficiency, which is defined as the ratio of minimum work required to the ideal COP or Carnot cycle. And here is its formula, that is evaporator duty multiplied by the temperature ratio and divided by the compressor work, and T naught is the reference steady state temperature, which is 25 degrees Celsius, and total exergy destruction is defined as the exergy destruction of all these components, and summing up all these exergy destructions. So it seems like correct. So here it has provided us the code, just like copy it and just paste it here, new file, Python, and just name it grok 7. Just paste this code and just run it and see it what it has done. So the code is running and it is calculating the state points, and here we can see the results. So here you can see how the COP is increasing as the evaporator temperature is increasing, and it should be increased because as the evaporator temperature increases, the temperature lift decreases, which increases the COP. And here is interesting thing, like with increasing in the evaporator temperature, the exergy efficiency is decreasing, and here is the plot with total exergy destruction with the change in evaporator temperature, which is saying that the total exergy destruction is also decreasing as the evaporator temperature is increasing. But from this plot you can see there is a contradiction between these two things. If the total exergy destruction is decreasing, so the total efficiency or the performance of the plant should, or the system should, increase, whereas here it is saying the exergy efficiency is decreasing. So these two things are a bit contradicting, which means like there is some error in the code. So we have to check the code and we have to see how it is calculating these. So here it has given the evaporator temperature, fixed condenser, and all other things are fixed. These are our refrigerants and the results. Here you can see the loop starts where the evaporator temperature is changing. So here it will run the loop and will save all these values. But what we want to see, and here it will make the Excel sheet, but we want to see the formulas it is using for calculating the exergy destruction and exergy efficiency. So here you can see there's the exergy destruction in each component. For the exergy efficiency, you can see it is Q evaporator divided by T naught divided by T evaporator minus 1. Exergy associated with cooling, and exergy efficiency is exergy out divided by total compressor work. So there is a error in this exergy efficiency formula, and usually the exergy efficiency is calculated by total exergy destruction and the total work. So but here it has taken this term exergy out, which I think is not correct. So what we need, we have to modify this exergy efficiency formula. Well, let's see. We'll go to Grok and ask the exergy efficiency formula is not correct, please modify it, and exergy efficiency is related with total exergy destruction and total compressor power. So now it will modify the exergy efficiency formula. So here it is saying like this is not capturing all the, you can say, the full picture, because you are calculating the total exergy destruction. So the point behind is for calculating all this exergy destruction of all the component is to calculate the exergy efficiency, whereas it was using only the evaporator parameters for calculating this value. So now here it has modified it, and this is what I want, is 1 minus total exergy destruction divided by the total work. So now it will modify it, and now it will calculate exergy efficiency in this way, which is the correct way. And the Exergy efficiency is changed. Excel output is changed. The loop is similar. It is running in the same way. Here you can see it is writing the code. So we'll just copy this code once it completed. Yes, so now we can just copy it, paste it, and we will see now what are the results. Yes, here we can see like as the total Exergy destruction is decreasing, the Exergy efficiency is increasing. It seems correct, but let's see uh, in detail. For example, here we can see for the ammonia, it is showing total Exergy destruction values and component wise Exergy destruction values. But here we can see that the Exergy destruction for evaporator is negative. So this is a red flag. It is not possible that the Exergy destruction should be negative. Let's also go to the saved Excel file and confirm it. For example, here it has saved the results for all the refrigerants. For our 134A, you can see the evaporator temperature change, COP, Exergy efficiency, total Exergy destruction, and you can see like for the compressor, condenser, valve, and these are all positive values, so it's okay. But for the evaporator, here you can see the Exergy destruction values are negative. Similarly, for all other refrigerants, we will check and we will see the Exergy destruction values for the evaporator are coming negative. So it means there is still some amendment needed in the code. So why it is happening? It is happening because for calculating the Exergy destruction for evaporator, we have to go to its formulae. Here you can see it is dividing it with evaporator temperature, but actually the refrigerator or the room which is to be cooled, its temperature is you can say greater than the evaporator temperature due to the temperature difference. So let's add, for example, 5 degrees Celsius change into the refrigeration space and the evaporator, and now we will run it again and we will see or the Exergy destruction for the evaporator has become positive or not. So now here we can see the values for the Exergy destruction for the evaporator is now positive value, and all other components are also positive. And here we can see the correct results. So here we can see with the evaporator temperature increases, the COP is increases, it's correct. And as the evaporator temperature is increasing, the Exergy efficiency is increasing up till a point and then it starts decreasing. So it's an interesting result. And here you can see as the evaporator temperature is increasing, the total Exergy destruction of the components is decreasing. So here you can see how we can evaluate the second law of thermodynamics, which is about entropy generation and which includes the Exergy. So we have evaluated the COP profile along with the Exergy efficiency and the total Exergy destruction. And here we can analyze at which point your system is behaving at its best Exergy efficiency. So we can see here at 0 degree Celsius of evaporator temperature, all the refrigerants are performing at their best Exergy efficiency. And yes, this Exergy efficiency is an important concept when we include the ambient temperature, because in the first law we don't include the boundary where your system is placed, and it does not includes the heat transfer with the surrounding, and it does not tell you the detail of the losses of the irreversibilities going on in the system. So this is the advantage of knowing the exergy efficiency and total exergy destruction. And in next video we will try to go more detail about what is this exergy destruction, and we will see in detail how the component wise exergy destruction is happening, and how each component is behaving as the evaporator temperature increases. So thank you very much for watching this video, and please like and subscribe my channel. Thank you.